Hi everybody, it's Mr. Sweeney here. I hope you're all doing well. In this video we're going to take a look at titrations. Titrations are a procedure that chemists do. They're pretty frequently done. So let's just get into kind of the definition first. Titration is a procedure done to determine the concentration of an acid or base solution using a known acid or base and pH indicator. So titration is a procedure. We're trying to figure out the concentration of a solution, and we're going to use the help of something called a pH indicator. So first of all, we have to kind of talk about what pH is. So the pH scale, if you've never seen it before, let's kind of take a look at that. Here's the pH scale. It goes from 0 down to 14, or up to 14, roughly. Right in the middle at 7 would be neutral, so it would be like pure water. Really acidic solutions have pHs close to 0. Battery acid, stomach acid in your body, getting a little higher, lemon juice, vinegar. Right at 7 would be your pure water, and then above 7 you got your basic solutions, or alkaline solutions. So blood is a little bit basic, baking soda, your stomach tablets that are trying to be antacids, right? They would create basic solutions to try and neutralize acid in your stomach. Soap, bleach, and then drain cleaner is really high on that end. So think of the pH scale kind of like a thermometer for acids and bases, right? On a regular thermometer, right in the middle temperatures, kind of like mid-range pHs, you're not talking about very dangerous pHs, right? Dangerous temperatures right in the middle of the scale. When you get closer to the ends, like really cold temperatures or really acidic solutions can be potentially harmful, just like really hot temperatures or really high alkaline or basic solutions can also be potentially harmful. You just have to be careful at the extremes of the scale. So let's go back over to our notes here. Titrations utilize neutralization reactions, which we know that's when you have an acid and a base reacting to produce water and some sort of salt. So what we're going to do in our titration is we're going to slowly add either an acid or a base to a solution of either a base or an acid. It doesn't matter which, as long as you're using an opposite, an acid and a base, or a base and an acid. And at a specific pH, the pH indicator, which would be in your solution that's having the acid or base slowly added to it, this indicator will change color. This is called the end point of a titration, when the color change happens. When does this color change happen? Well, let's take a look at some pH indicators and the pH ranges at which they change color. So for example, if you're looking at crystal violet up here at the top, it changes from a yellow to a blue between pHs of 0 to 2. Okay, really acidic solutions. Moving towards the middle of the scale, bromthymol blue is a pretty popular pH indicator. It goes from yellow to blue right around 6 to 7 pH. In high school labs, phenolphthalein is probably going to be your most prevalent pH indicator, just beyond neutral solution. So as soon as you get above 7, bordering right on pH of 8, it's going to go from light, completely clear solution to a light pink. And so that's a really good pH indicator to know when you've gotten right around that, just past beyond the pH of 7. Shift back over to our notes. And for many titrations, this color change occurs when the acid and base have neutralized each other. This is called the equivalence point. It's called the equivalence point because you essentially combined equal moles of acids and bases. So let's take a look at the equipment that you would use in a pH or in a titration. You get to use a burette, which is this tall, skinny piece of glassware that would have graduations all along the edge for you to read volume. You would use an Erlenmeyer or a beaker down at the bottom where you would contain your unknown concentration of solution. And in your burette, you're going to put your concentration of either the acid or the base that you know the concentration of. We call this the titrant. And you're going to read the initial volume of your titrant and your final volume, and that way you can subtract the two to get how much of that titrant you used. Burettes are actually interesting in that they're set up in reverse order of what you would assume. You would assume that the 100 is at the higher volumes to be at the top and lower volumes at the bottom. It's actually written in reverse. Most of the burettes that you would use hold about 50 milliliters of liquid. So the 50 is actually at the bottom, somewhere around here would be 50. And 0 would be somewhere towards the top, not exactly at the top. So they're written in reverse order. Anyways, you've got this little lever here that's called either a stopcock is one name for it. You could just call it a valve if you wanted to. You turn that just a little bit so you get a drip, drip, drip. You don't want to stream because you want to really accurately measure the volume that you're adding to this analyte down here. Because we're looking for this color change, and we don't want it to be a really dark color change. We want to know, let's say that our solution is going to turn faint pink. Well, we want drop, 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 so that as soon as it turns pink, slightly pink, we can close the valve, close the stopcock, and then we can accurately record our volume that got us to the end point. If you have a stream of titrant, you're not going to stop it accurately, and you're going to have a poor measurement of the volume needed to get to that endpoint. The indicator in here, you would just add a few drops before you began the experiment of indicator into your analyte down here before you got going. One thing that a lot of scientists need to keep track of is the pH of their solution as the titration is happening. So let's take a look at some titration curves. So I want you to take a look at this top right curve first. This is when you're reacting a strong base with a strong acid, and we're starting with base in our Erlenmeyer flask at the bottom, and we're dropping in strong acid. So our pH at the beginning of the titration starts out really, really high at the 14 because it's a very strong base. As you add the acid, that pH starts to lower a little bit, and then boom, it drops off. This point where you're right in the middle of this vertical component of the line, this signals the equivalence point. When you got equal moles of your acid and your base. And at the equivalence point for a strong acid and a strong base, you're right at the pH of 7. You've completely neutralized your acid and your base, and you reach a nice neutral solution. If you look at the graph to the left, you're starting with a strong base again, but this time you would be adding a weak acid solution. And what happens is this equivalence point happens above a pH of 7 because your acid is not as strong as your base. Weak acids do not completely break apart or dissociate in water. They mostly stay together with the hydrogen attached. Strong base, not the case. These are when they completely ionize, like sodium hydroxide completely breaks apart into Na+ and OH-. Long story short, your pH will be slightly basic at the equivalence point. Bottom left graph, opposite thing is happening here. You're starting with a weak base. Your pH is not all the way up at the top. Add your acid, and at the equivalence point, your solution is acidic. And we won't really worry about the weak base, weak acid. That's not a very popular titration. A couple of other titration curves you may see might look like pH. It's got two steps, has two equivalence points. This would be for something called a diprotic acid. Diprotic means two hydrogens, like H2SO4. It's got two hydrogens that can be removed. We call it diprotic. It's called protic because an H+ ion is essentially just a proton because it doesn't have an electron and no neutrons. So it's just a proton. So diprotic acid would be H2SO4. Similarly, if you get a pH curve that looks like this with three equivalence points, that's for each of the three protons being removed, something like H3PO4. This is a triprotic acid. So let's jump into an actual math example here. Let's say we're doing a titration where we've got our burette set up. The volume of our base starts out at the 31.2 mark. We're titrating our acid down here that we're trying to figure out its molarity. And so we add our volume of calcium hydroxide, and the volume ends here, and that reaches us to the end and equivalence point, and we're trying to figure out this molarity. So I've got our balanced reaction written over here, and if you subtract these two volumes, you'd find out how much was actually added. That would be 12.5 milliliters. And so we've got a stoichiometry problem here. We've got 12.5 milliliters of our CaOH2. I'm going to train track my way to moles of HI. So 1,000 milliliters in a liter, and in 1 liter of our calcium hydroxide solution, we would have 2.0 moles of CaOH2. That's just using the molarity of the calcium hydroxide. Next, I can use my mole ratio. There's 1 mole of CaOH2 for every 2 moles of HI, which gives me 0.050 moles of HI that got neutralized. So then to find the molarity, I can just divide the moles, 0.050 moles of HI, by the volume of HI we started with, which was 0.100 liters, giving us a molarity of 0.50 molar HI. Since we reacted a strong base, calcium hydroxide, with a strong acid, hydroiodic acid, that means that our equivalence point would be right in the middle, and we should use a pH indicator that changes color just after that equivalence point. So our graph would be pH, here's 7, here's 14, here's 0. We started with HI, so the pH would be really low. Equivalence point right here in the middle. And a good indicator would be phenolphthalein, because phenolphthalein is clear and pH is below 7. And just above 7, you get this pink color indicating that you've reached the end point of the reaction and the equivalence point.